Hi, my name is Elizabeth Russell, and this is my lab report for Lab 4 oscillations. In this lab, I studied the motion of a spring mass system that both swings and stretches at the same time. I used Tracker to analyze the video and GlowScript to model that motion computationally. The purpose of this lab was to understand how a spring mass system moves in two dimensions and to see whether the energy principle holds true. I also compared the motion measured in the video to the motion predicted by my computer model to see how well theory matches experiment. So these are the equations that I used. The motion can be explained using Newton's second law and the energy principle. We have net force, position update formula, and velocity update formula, and then the energy principle where we have delta E equals work done by surroundings plus heat, and then delta E equals delta K plus delta U gravitational plus U spring, which are potential energies. And then I have the actual formulas listed for those things. These equations describe how energy shifts between different forms as the spring moves. For the experiment, I used the video listed in the lab instructions and analyzed it in Tracker. I calibrated the video using the meter stick in the frame, and I tracked the X and Y position of the mass throughout the motion. The time between frames and physical constants like mass, spring constant, and relaxed length were taken from the pre-lecture video, so they were provided. The mass for this specific experiment was 0.402 kilograms. And then I have the results of that on the right, which shows the oscillation. So these are the initial conditions in my code. I used the data from Tracker to then put into my code. The initial position and velocity were taken from the first few Tracker data points. Velocity is 0, so yeah. In the code, I set a small time step for accuracy and calculated the net force on the mass at each instant based on spring and gravity forces. So here you can see that I used the energy principle to calculate the system's energies. And then again here, which then I used the gravitational force, spring force, the Newton's second law, and applied it all to get accurate data. And here were the results that I encountered. This plot shows how different types of energy change with time. The blue curve is the change in kinetic energy, red is gravitational potential energy, green is spring potential energy, and the yellow line shows the total energy, yellow/orange. While individual energies go up and down, the total energy stays nearly constant, proving that the energy principle is satisfied. Small variations in total energy come from tracking errors, air resistance, and rounding in the model. And then here I have the comparison of my tracker information versus the computational model. Here we see the X position and Y position of the mass over time. The red line represents the experimental tracker data, and the blue line is the computational model. Both show oscillating motion with very similar shapes and timing. Small differences in amplitude or phase are likely caused by experimental errors or simplifications in the model, like ignoring friction. Overall, the model accurately predicts the real motion of the mass. So, what does this mean? In summary, the total energy remained constant, showing that energy was conserved. The model and experiment matched closely in both directions. This confirms that our energy and motion equations accurately describe the 2D spring mass oscillation. So, is the energy principle satisfied? Yes. The total energy stayed constant while kinetic, spring, and gravitational energies exchanged. That means the energy principle holds true. Comparing the oscillation periods from X and Y, by measuring the time between peaks, both X and Y directions had similar periods, about 1.3 seconds. Any small difference is due to measurement noise or coupling between horizontal and vertical motion. So both directions oscillate with roughly the same time period, confirming the model's accuracy. To conclude, this lab showed that the spring mass system's motion can be predicted and explained using energy principles in Newton's second law. The experimental data and computational models support each other, showing that total energy is conserved and the system behaves as expected. Thank you.